Okay, so in this problem, we have Bessie playing hide and seek with some cows. This game takes place on n farms connected by n-1 pathways. And each pathway connects two distinct farms, and there is a unique path between any two farms. And the path can be traversed in either direction. So the game starts with Bessie making a move. Bessie can either stay on her current farm or move to an adjacent farm connected by a pathway. The game alternates between Bessie taking a turn and the other cows. So after Bessie moves, all the other cows take a turn simultaneously, and they can again either stay on their current farm or move to an adjacent farm that is connected by a pathway. The game ends when Bessie is caught, and Bessie is caught if any cow ends up on her farm. Her goal is to survive as long as possible without getting caught. And given that all the cows play optimally and have full information, we want to know the maximum number of turns that Bessie can stay in the game. Great. So if we look at the first example, we have 3 farms. 1, 2, 2, and 3. Bessie is currently on farm 3. And there is a path between farm 1 and 2, and 2 and 3. And there's also a cow on node 1, farm 1. So if we look at this and both of the cows play optimally, at time 1, Bessie would stay in place, and cow would move from node 1 to node 2. Now on time 2, Bessie would again stay on her node, and the cow would move from 2 to 3 and catch up to Bessie. So if we look at the output should be 2. Now let's look at a different example, the second test case in the input 1. We have 4 nodes. So we have 1, 2, 3, and 4. Bessie is currently on node 1. And the cows are on 2 and 3. And there are paths here. Oh. There are paths between 1 and 2, 1 and 3, and 1 and 4. So if we look at this, if Bessie plays optimally, Bessie would move on time 1. Bessie would move to node 4, while afterwards, the cows would move from node 2 to node 1, and from farm 3 to farm 1. Now on time 2, Bessie would stay in place on node 4, while both of the cows would move to farm 4 and catch up to Bessie. So the output for the second test case is also 2. Great. So let's just consider the first case, where we only had 1 cow. The strategy for this cow would always be to go towards Bessie. If Bessie gets caught at node U, it's possible to show that the cow took the shortest path to U. So in this first case, the cow obviously only has 1 path to go, from 1 to 2 and 2 to 3, and this is the shortest path. And so we can do a BFS from the cow to find the distance from the cow to each location. So on the first example, the cow is distance 0 away from farm 1, distance 1 away from 2, and distance 2 away from 3. And if we did the same for Bessie, Bessie is 0 away from 3, 1 away from 2, and 2 away from 1. Yeah, so we do the same BFS for Bessie. If Bessie can go to a location at time t if the distance from Bessie is less than or equal to t, since she can move to a location and stay there. And she can continue from the location if the distance from the cow is, or the distance from Bessie is less than t, since she can keep moving and it's not yet equal to t. Now, for this solution, we can compare every single node where the time for Bessie to get to the farm is less than the time for the cow to get to the farm. So here we can see that only one farm actually meets the criteria, which is farm 3 over here. Since Bessie takes 0 time to get to the farm, and the cow takes 2 time to get to the farm. Actually, we would also have to consider the time where Bessie and the cow get to the farm at the same time, since Bessie actually moves before the cow. So this case would also work. Since Bessie takes 1 time to get to the farm, and then the cow takes another 1 time to get to the farm. And to actually get to the answer, we just take the maximum of the cow's time. So in this case, we take the max between 2 and 1, which would be 2. And as we can see, the output is 2. Now we can generalize this to a case with many cows, since the only difference is that instead of just adding 1 cow to your BFS, we add multiple cows. And this is multi-source BFS. So in this case, for the second example, we can add both the cows on farms 2 and 3 to our queue. And we can see that the distance to the nearest cow is 0. Now we can move to the next node, and we see that at farm 1, the nearest cow is 1 time away. And node 4, the nearest cow is 2 times away. And if we did the same BFS for Bessie, orange, we can see that Bessie is 0 time away from node 1, farm 1, and 1 time away from all the other farms. So again, we look at every single farm where the time for Bessie to get to the farm is less than or equal to the time for a cow to get to the farm, which is the nearest cow. And in this case, we see that farm 1 and farm 4 meet this criteria. And so we just find the maximum time for a cow to reach the node. Yeah, the maximum time for the cow to reach the node. And in this case, we again take the max between 1 and 2. And so the output, as you can see down here, is 2. Great. And that is how you do the problem.